Hey guys, this is Carl from University at Buffalo, and recently I hear a lot of people talking about machine learning stuff, and it's a very interesting topic, and there are lots of applications and frameworks you can find to do the machine learning, even though you don't know too much about the programming like me. So today I want to talk about how we can benefit from machine learning in physics. That is using the machine learning methods to analyze the G2 correlation data. So first, let's have a quick review about machine learning. So compared to a traditional programming method, which in general, we write a program to analyze the data and get an output. But for machine learning, there's an interesting switch. So we input the data with an expected output into the computer. So it can study the pattern and gets enabled to analyze the new data. And a quick example would be identifying those dogs and cats pictures. They're really cute. So we let them go through those intermediate layers, and the computer can figure out a set of functions and choose the best one to map from the input to the output. And then we can use this function to detect a new picture. So the computer will tell us, is that a dog or a cat? And similarly, this technique has been used in such as classification, like an email spam filter, or a regression, like they use in stock market or predicting the weather, and tons of other applications. So as physicists, we are trying to apply this technique into the physics research, which brings us to the next topic, the single photon source. So a quantum dot is usually considered as a single photon emitter, and we can use pulse excitation to generate one photon at a time. And in that way, those single photon sources have its famous anti-bunching behavior. That is, we can see compared to a coherent laser, a single photon source, one pulse can only contain one photon. And this feature has make the single photon source to become an essential part in most of the quantum communication systems. And to detect such a single photon source, we can actually use its anti-bunching nature. So in the so-called HBT measurement, we use a 50-50 beam splitter, which can equally split the incoming photons. So as you can see, the photon goes into either detector 1 or detector 2. And then we can correlate those two detectors to figure out a correlation to figure out an intensity correlation function, or so-called G2 function. And if you Google a G2 measurement, you probably will end up something with those experiments related to measuring muon. I think it's about the magnetic dipole moments about muon. So that's definitely not in our case. So a G2 function generally can tell us that if we have already detected one photon at time t, then what is the probability to get another photon at time t plus a time difference tau? And in this figure in the right, we can see for a single photon source, when the time difference tau becomes 0, the G2 goes to 0 as well. So this means those two detectors, they can never detect a photon at the same time. And experimentally, if the G2 at 0 point is lower than 1/2, then we can say it's a single photon source. And the main challenge here is that since our incoming light has such a low intensity, then the time for the measurement and data analysis is significantly low. So is there a way out? And the answer is machine learning. So just like what we did for those dogs and cats pictures, we can actually dump our G2 data in a well-designed convolutional neural network. And then we just let the computer to do its job. And after the learning process, we can input the actual target data into this model. And then we can get output. So this method will be way faster than most of the traditional data analysis methods. And we have a little wish list for the future. One is we're trying to get this feedback in real time or quasi-real time. And next, we'll expand this model for higher order correlation. And also, we probably will combine with some statistical learning methods such as Bayesian model to get more speed up. And you are also welcome to visit my repository, which is G2-Coral under the UB-SUNY. And in this repository, first you can go to the wiki, where you can find some related information, such as about the physics background and the Bayesian model we will be using, and something about the TPU. This is Coral, which I am using for this project, and some other parts that needs to be finished. And if you go to the branch model, you will see some codes such as the SDT reader, which is for reading the data files, and also some Python files I just write for, to analyze the data. And there's a notebook. Once you open it, you can find more details, such as those are importing libraries and make plots of the G2 data we have. And then comes the machine learning part. So this is our model. And next is the training process. And then we can take a look at those training and validation loss. And then we make a prediction to get this and this prediction. And since this is just a milestone, and you can see we have a lot of issues that need to be solved. So hopefully by the end of this semester, we will make more developments and improvements.